Alright everybody, this is going to be another instructional video right here. It's going to be a little demonstration. What I want to prove here is basically how a loss of electrical power works over a distance. Now let me show you what I've done here. I've disconnected my power supply and all I have connected is my battery. Okay, this right here is power and ground. This is running directly into my AC/DC clamp meter here. So we are seeing 13 and 15/100ths at the battery. That's 13.15 volts. This meter over here is running directly into the actuator of the door. Okay. Now right now we're not seeing any power because I'm running the wires from the door into this huge spool right here. This is approximately 40 feet of wire. It's a 14 gauge, approximately 40 feet. So I'm running this to the door and then it's going to go directly into the battery. What I want to show you here is the amount of loss, the tremendous voltage drop that takes place over distance. So, there we have my ground connected. This is going to be my power. I'm going to connect this and I'm going to go to the meter so you can see the left meter is showing power at the battery and the right meter is showing power at the door, the measurement at the door. I'm going to show you the loss over distance. My guesstimation should be maybe 4-5 volts at the door. Let's see what we got here. It'll barely be enough to even make the window move. Ready, set, go. Okay, window's not even budging. 1293 at the battery, 4 volts at the door. Disconnect, reconnect. 4 volts, not budging. You can hear the motor trying to. Hear that? So, okay, so 40 feet of wire right there. There's such a tremendous loss as far as voltage, it's not enough to even activate the door actuators. Now, next thing I'm going to do here is I'm going to disconnect this long spool of wire, and I have a little 6-foot run that I just cut. Let me find it. Here it goes over here. Here's a little 6-foot run. Now I'm going to run this 6-foot run directly into the door. So I'm going to disconnect this. Pull my alligator clip off. Okay. Okay, now moving along to part 2 of this demonstration. I now have the little 6-foot run right here and right here, running directly into the actuator of the door over here. Okay, same meter. This is measuring the voltage at the door. This is measuring the voltage at the battery. The large 40-foot spool is sitting over here on the chair. Let me show you how this works. Okay. Okay, ready? Going over here to the meters and go. Okay. Let me reverse the polarity real quick. Okay. Alright, we're looking at 12.9, almost 13 the battery. And here we go. Reverse the polarity one more time for you. It's not easy doing all this crap with one hand. Give me 1 second. Hold on, fellas. Okay, let me do this one more time. 12 died the battery, and that's the door. So, that right there is showing the difference between a 6-foot run of 14 gauge and a 40-foot run. Okay, so now what I'm going to do is show you how electricity does in fact follow the path of least resistance. So, what I'm going to do is take the 6-foot run and the 40-foot run and connect it both to the actuator of the door and the battery. Okay? Now I have the 6-foot run connected. We're running into the door. I also have the 40-foot run connected as well. Okay? So we have the 6-foot run connected and the 40-foot run connected. splicing together up here. These other ones right here. Now I'm gonna go over to the meter and we'll see what we're getting here. We're at 13 at the battery, and let's see. Ready, set, go. Seeing 11 and change at the door. So, what this here proves is, and this showing you that it is connected, okay? What this is showing here, fellas, is that before, where we had this long 40-foot run connected by itself, you couldn't get enough power or current to transfer through the wire to get the door to even work. By adding this little 6-foot run right here, now there's enough power getting through. That's because electricity does in fact follow the path of least resistance, which will be over this little 6-foot run right here. Next thing I'm going to do is I'm going to take my clamp meter and go ahead and clamp the power wire on the 6-foot run, and then I'll clamp the power wire of the 40-foot run and show you how much current is actually traveling through each wire for comparisons. Okay, now I've got the clamp running around the 6-foot run, running around the power wire. So now we're going to clamp how much power is actually running through there. Alright, 1, 2, 3, go. Alright, we're seeing at a peak of about 8 amps. Okay, now we have the clamp running around the 40-foot run. Okay, that again, still the voltage. Everything's still connected the same. The 6-foot run is now loose. It's still connected, but it's not in the clamp. So we're clamping just the 40-foot run. And here we go. Let's see. So we're seeing less than an amp of current running through the 40-foot run. In closing, some of you may be wondering, what does all this mean? What does this mean for you? Basically, it means that when you see wiring like this, it's not overkill, fellas. This right here is my relay. It's capable of switching about 40 amps of current. So you see I have 4 runs going to each of the 3 tabs. This is simply my remote turn on here. Then I have 4 runs going to my ground, 4 runs going to my power in, and 4 runs going to my power out. It's really not overkill, although it may seem like it is. Heavy duty connections like this, fellas, are truly what's necessary for doing what we do. I mean, the name of the game here is efficiency. So in running my own wires, I'm seeing a far greater efficiency compared to the original factory bullshit wiring that was connected before. There were literally hundreds of wires, and yeah, just a bunch of bullshit, basically. So, like I mentioned previously, fellas, efficiency is in fact the name of the game. That's what it's all about. Alright, y'all. I hope this little video, hope you guys are able to take something away from it and hopefully use it. Alright, y'all. More to come. Peace.